Hi friends, once again welcome back in our educational channel, that is Precise Electronics. Friends, in previous video lectures we have studied the types of counters, that is asynchronous counter, which is also known as ripple counter. The next type is a decade counter, that is mod 10, modulus 10, it is mod 10 counter, that is also known as decade counter, and ring counter, which is basically shift register. And in this video lecture, we are going to study the next type of counter, that is synchronous counter. Now friends, what is synchronous counter and why the synchronous counter is used? The synchronous counter is known as parallel counter. Why it is called parallel counter? Because in this counter, the clock input is connected to the all flip-flops. While in asynchronous counter, the output of first flip-flop drives the clock input of second, clock input of output of second drives the clock input of third, and so on. But in this case, the clock input is connected to clock input terminals of all flip-flops at a time. So they are clocked simultaneously. And because of this, the speed of operations, the speed of counting increases, and which is basically a drawback of synchronous counter. Drawback of asynchronous counter, that is ripple counter. What is the drawback of asynchronous counter or ripple counter? That is speed of operation, the speed of counting. And obviously, to eliminate this drawback, the one more counter is designed, and that is synchronous counter, that is parallel counter. In this case, we are going to study 4-bit synchronous counter. So obviously, in this case, the 4 flip-flops may be required. So the logic diagram of synchronous counter is now going to display on your screen. From this diagram, it is clear that 4 flip-flops are used because it is a 4-bit synchronous counter. So this counter is able to count the 16 pulses, 16 clock pulses, or it count the 16 stages, because m, that is modulus, is equal to 2 raised to n. In this case, n is a flip-flop, number of flip-flops. So in this case, the 4 flip-flops are used. So obviously, m is equal to 2 raised to 4, that is 16. So modulus of this counter is 16. So it is mod 16 counter. This counter can be able, it is capable to count the 16 stages, and after that it will get reset and start counting from its initial stage. So in this circuit, from this logic diagram, it is clear that the 4 JK flip-flops are used. J and K input of first flip-flop short circuited and connected to the plus VCC. So obviously the first flip-flop is in toggle mode because both J and K are connected to the plus VCC. So first flip-flop is in toggle. The output of first flip-flop, that is A, drives the J and K inputs of second flip-flop. Clock input of second flip-flop is also connected to the clock inputs, that is input frequency, clock frequency. But J and K input of second flip-flops are short-circuited and they are connected to the output of first flip-flop. So output of first flip-flop drives the J and K of second flip-flop. The output of first flip-flop, that is A, is also connected to AND gate. The second input of AND gate is the output of second flip-flop, that is B. So the input for AND gates are A, B, whose output is now A dot B, is connected to the J and K input of next flip-flop, that is the third flip-flop, C flip-flop. The output of AND gate is also connected, that is A dot B, is connected to the next AND gate. The 2 AND gates are used in this case. The output of first AND gate, that is A dot B, is connected as the input of next AND gate, and the second input of that AND gate, that is the second AND gate, is the output of third flip-flop, that is C. So output of third flip-flop is connected to the second input of AND gate, whose inputs are now A dot B and C, whose output is A dot B dot C, and that output is connected to J and K terminals of fourth flip-flop. So from this it is clear that the output of first flip-flop drives the J and K input of second flip-flop. Output of first and second flip-flop drives the J and K input of third flip-flop, and so on. So that means the output of previous flip-flops are connected to J and K input of the next flip-flops. In this case, the clock input is applied to all flip-flops at a time, and in this case, bubble is missing, so obviously it is positive edge trigger JK flip-flop. So transition of state occurs at the positive edge of input clock pulse. All flip-flops are made clear by using a clear pulse. Once again, the active low clear pulse is required. So when we are applying a low clear pulse, the all flip-flops get reset. So the output of flip-flops, output of counter at the initial stage before applying any clock pulse is 0, 0, 0, 0. That is 0, 0, 0, 0. So that is initial stage of our counter. Now how counter progresses, how counter count the pulses. When the first pulse is applied, before applying first pulse, the all flip-flops are made clear. So output of counter is DCBA is equal to 0, 0, 0, 0. Next, when the first clock appears at the positive edge of clock pulse, the first flip-flop toggles. Because it is already in toggle mode, so transition of state occurs at the positive edge of the first clock pulse, and due to which the output of first flip-flop, that is A, changes from low to 1. While the output of remaining flip-flops remain as it is, they remains in a last state. Hence, the output of counter at the first clock edge is DCBA is equal to 0, 0, 0, 1. That is our first stage. Next, when the next pulse applies and the next positive edge appears, once again A flip-flop toggles and changes its state from 1 to 0. The first flip-flop changes its state from high to low. At the same time, the clock pulse is also connected to the B flip-flop, C flip-flop, D flip-flop. B flip-flop changes its state because when the first clock applies, the output of first flip-flop, that is A, goes to high level. That means first flip-flop is in set mode. That means J and K input of second flip-flops are already connected to high logic. So obviously the second flip-flop is in toggle mode. So before applying a second clock pulse, the second flip-flop, that is a B flip-flop, is already in toggle mode because the output of first flip-flop is high. The first flip-flop is in set mode. The second flip-flop is in toggle mode. So when the positive edge of the second clock is appears, the output of A changes from 1 to 0, but the output of B changes from 0 to 1. So the transition of B flip-flop occurs, its state changes from low to 1, while C and D flip-flop remains in a last state. So the output of counter at the positive edge of second clock pulse is now DCBA is equal to 0, 0, 1, 0. 0, 0, 1, 0. Next, the next pulse applies. When the next pulse appears, once again at the positive edge of input clock pulse, the first flip-flop is in toggle mode. The transition of state occurs and the output of first flip-flop changes from low to 1, low to high, 0 to 1. But this positive edge, the third positive edge, will not affect the state of B flip-flop because before applying the third positive edge, the output of A is low. So obviously the A flip-flop is in reset mode because output is 0, 0, 1, 0. So A is in reset mode, due to which the J and K input of second flip-flop, that is B flip-flop, are in low, 0 pulse. They are in low state. As J and K inputs are low, the flip-flop remains in last state, and in this case, the last state is a set state. So the transition of B flip-flop will not occur. A flip-flop changes its state from 0 to 1, B remain as it is, C and D are also remain in last state. So output of counter at the end of the third pulse is 0, 0, 1, 1. 0, 0, 1, 1. Now, as A and B flip-flops are in set mode, output of A flip-flop is high, output of B flip-flop is also high. So what is the output of counter at the third clock pulse is 0, 0, 1, 1. As both A and B outputs are high, the output of AND gate is high. That means, friends, in this case, the third flip-flop, that is C flip-flop, is in toggle mode. The third flip-flop is in toggle mode. When next clock appears at the positive edge of the fourth clock pulse, A flip-flop changes its state from 1 to 0. B flip-flop also changes its state from 1 to 0 because B already is high. Sorry, A is already high. So B flip-flop also in toggle mode. So B flip-flop changes its state from 1 to 0, and C flip-flop is already in toggle mode because A and B are at set mode. So C flip-flop is in toggle mode. So when the fourth clock pulse appears at the positive edge of the fourth clock pulse, A changes state from 1 to 0, B changes state from 1 to 0, but C changes state from 0 to 1. The output of third flip-flop goes to high level. So third flip-flop is in set mode. So output of counter at the fourth clock pulse is DCBA is equal to 0, 0, 1, 0, 0. 0, D remain as it is 0. Transition of C occurs, it changes from 0 to 1. B, transition of B occurs from 1 to 0. C, that is also changes from 1 to 0. So output of counter at the fourth clock pulse, at the positive edge of the fourth clock pulse, is now DCBA is equal to 0, 1, 0, 0. This process remain continue. With every clock pulse. The next flip-flop changes its state only when the previous flip-flops are in set mode. The transition of state occurs only when the both J and K input of that particular flip-flop becomes high. It goes to high level, and that will happens only when the previous flip-flops are in set mode. That means transition of B occurs when A is set mode. Transition of C occurs when both A and B are in set mode. And transition of D occurs when both A, B and C are in set mode. So that means from this we can conclude that the flip-flop, the transition of flip-flops occurs only when, or the flip-flop is in toggle mode, or the transition of state occurs only when the previous flip-flops are in set mode. So that is 4-bit synchronous counter. Now we are moving toward the clock diagram of 4-bit synchronous counter. First of all, just look at the clock diagram, and then after we are going to study how that clock progresses. So give 1 or 2 minutes, concentrate on this figure, on this picture, on this movie, how this clock pulse passes, how this clock pulse progresses, and how the flip-flops changes its state from 0 to 1 or 1 to 0. That means how the transition of state occurs. So friends, keep watching this clock diagram, and afterwards we are going to know for explanation. First of all 16 clock pulses are going to display on your screen. In this case, the flip-flop is positive edge trigger flip-flop. So the positive edge is applied, and that positive edge are indicated by upward arrow. The upward arrow is there, and that upward arrow indicates the state of that clock pulse changes from low to high. Next, before applying clock pulse, all flip-flops are made clear. So the output at the initial stage is 0, 0, 0. So first A, the output of A remains low. Next B, output of B also remains low. Next C, the output of C also remains low, and next D, output of D also remains low. So all flip-flops are in reset. Now we are going toward the clock diagram of first flip-flop. How the transition of first flip-flop occurs. At the positive edge of the first clock pulse, the A flip-flop, the changes its state from 0 to 1. B and C remain unaffected, so it remains as it is. Next, at the positive edge of the second clock pulse, at the positive edge of second clock pulse, the transition of A occurs. It changes the state from 1 to 0. As A flip-flop is in set mode, the output of A remains high. The B flip-flop is in toggle mode. So at the positive edge of the second clock pulse, B also changes its state from 0 to 1. So output of B changes from 0 to 1. Next, when next pulse appears, that is the third clock pulse, at the positive edge of third clock pulse, A changes the state from 0 to 1, but B remain as it is. When the next positive appears, output of C and D remain as it is. So at the fourth clock pulse, A changes the state from 1 to 0, B also changes its state from 1 to 0, and C is now in toggle mode because A and B are in set mode. Before applying this pulse, A and B are in set mode. So the third flip-flop is in toggle mode. In the transition of third flip-flop appears, and the output of third flip-flop is C changes from 0 to 1. So this process remain continue, and the clock moves through each flip-flop. That is the clock diagram. At the 8th clock pulse, the output of A flip-flop changes from 1 to 0. B also changes from 1 to 0. C also changes from 1 to 0. As before applying this clock pulse, the output of all three flip-flops are high. Therefore, the fourth flip-flop, that is the D flip-flop, is in toggle mode. Hence, the transition of state occurs. That is, A changes from 1 to 0, B changes from 1 to 0, C changes from 1 to 0, but D changes from 0 to 1. So this process now remain continue, and at the 16th clock pulse, the A changes the state from 1 to 0, B also changes the state from 1 to 0, C also changes the state from 1 to 0, and D also changes the state from 1 to 0, because once again A, B and C, all three flip-flops are in set mode. Therefore, J, K input of fourth flip-flop, that is a D flip-flop, are connected to the high logic. So the fourth flip-flop is in toggle mode and the transition of state occurs. So at the 16th clock pulse, the output of first flip-flop changes from 1 to 0, goes into reset mode. B also changes from 1 to 0, C also changes from 1 to 0, and D flip-flop, that is the full flip-flop, also changes the state from 1 to 0. That means the output of counter at this stage, at the 16 clock pulse, is 0, 0, 0, 0. D 0, C 0, B 0, and A is also 0. And that is our initial stage. So when the next clock appears, at the positive edge of the next clock pulse, the counter start counting from its beginning. So that will be the first pulse, and the output of counter will be 0, 0, 0, 1. That is our first stage. So that is the clock diagram, or that is known as the timing diagram of this counter, that is the synchronous counter. Now friends, we are moving toward the truth table of synchronous counter. The truth table of synchronous counter is now going to display on your screen. The truth table of synchronous counter is same as truth table of asynchronous counter, because both this counter count the 16 pulses. It count the 16 stages. So before applying clock pulse, all flip-flops are made clear. So output of counter is 0, 0, 0, 0, D, C, B, A, 0, 0, 0 and 0. When the first clock appears, the output of counter is 0, 0, 0. Second, it is 0, 0, 1, 0. Third, it is 0, 0, 1, 1. Fourth, 0, 1, 0, 0. That means with every clock pulse, the bit counted progresses by 1, increases by 1. So at the 16th clock pulse, at the 15th clock pulse, the output of counter is 1, 1, 1, 1. 15, that is 1, 1, 1, 1. So at the 16th clock pulse, the all flip-flops get reset. So output of counter is 0, 0, 0, 0. That is our initial stage. And when the next pulse appears, that is pulse number 17, the output of counter is now 0, 0, 0, 1. It starts counting from its initial stage. So friends, that is synchronous counter, which is known as parallel counter, in which all flip-flops are clocked simultaneously due to which the speed of counting, speed of operation increases, but the components required, that is the hardware used to assemble this counter, are more than the asynchronous, that is ripple counter. So friends, this is synchronous counter, that is parallel counter. So in the next video lecture, we are going to study the next type of counter, that is down counter. So friends, keep watching our video lectures. Bye, take care. Once again, thank you. See you again.